The mismatch bases will follow the majority consensus, meaning that the probe will have the most common base within the alignment. This design minimizes cost, an important consideration, especially in diagnostic assay design. If the homology between the aligned sequences is low and it is not possible to design assays with a single probe for each taxa, even after tolerating mismatches, the minimal set option comes to your rescue. Allele ID then designs the minimal number of probes required to identify each taxa. Each probe will be completely homologous to the sequences to which it binds, and all probes together will identify the taxa even when there is not enough consensus among them all. This is an important option for studies involving phylogenetic relationships among sequence groups which have two or more highly conserved subgroups. For example, the same taxa evolved in two or more different geographical locations. Let us now search for a minimal TaqMan set with optimal primers. Allele ID has designed a set of 2 probes to identify 10 sequences. The assay can be viewed by clicking the probe details in the multiple sequence alignment view or clicking the minimal probe matrix tab on the properties pane. A plus sign in the minimal probe matrix indicates that the probe detects the sequence. A Y in the status column indicates that a sequence can be uniquely identified by using one or more probes. At times, you may want to reuse pre-designed primers or primer pairs from your lab or the literature for some of the sequences in the alignment. With Allele ID, you can design primer pairs for the rest of the sequences compatible with these pre-designed primers. Select the alignment from the Aligned Sequences table. Go to Analyze, Load, Pre-designed Primers, and select Species-Specific Evaluation, or Taxa-Specific Cross-Species Evaluation, or click the button. Type or paste the primer sequence in the text field. To specify more than one primer, click the button to expand the field. Paste the primer sequences in the window and click Add. You can add just sense primers, antisense primers, or pairs for any alignment. Launch a search. The results are displayed in the Properties tab. Notice that the new sense primers are displayed in blue and the new antisense in pink as usual. The pre-designed primers you added are in gray. If the pre-designed primers are not entirely homologous to the template, you need to specify an acceptable number of mismatches in the advanced parameters. If the primers you entered are not homologous to either of the sequences within the acceptable mismatch limit, Allele ID does not use them. Instead, it designs new primers. Alignments can be saved as .aln files. A web page containing alignments with oligos can be created for saving or presenting your results. Go to File, Export, Alignment, or Alignment with Oligos. To export the design results, right-click the Properties pane and select Export to File. Exon data is required for designing primers for selective cDNA amplification while avoiding gDNA. It is frequently available in GenBank sequence headers. When you download a sequence from Entrez containing exon information, Allele ID automatically loads and displays it in the Exon Information tab. Either the sense or antisense primer is designed across one of the specified exon-exon junctions. If the exon information is not in the GenBank file, you can easily add it. Select the sequence, go to the Tools menu and click Exon, Locate Exon. Type the from and to position and click Add. The added exon is displayed in the Exon Information table. For example, let us start with this sequence. Select Analyze, Exon Junction Primer Search, or click the button. Allele ID has interpreted the available exon information in the sequence header and presented it for your selection. Select one or more exon junctions and click the Search button. The junction spanned by the primer and whether the primer is for the sense or antisense strand is displayed in the status line of the Exon Information tab. If you have a large amount of unpublished exon information, you can load it into allele ID by converting it into a GenBank-like format. We provide a template for creating such a file in the Load Exon section of the online help. Copy and paste the template in the Notepad editor. The locus and accession numbers are generally the same, but you can specify any value for locus. Number of BP is the number of sequence bases. Add all the exon locations as exon features in the required format, then paste in the sequence. It must start with a new line and end with a double slash. The program's powerful BLAST facility interprets the results of fast, multi-threaded BLAST searches and uses them to design specific oligos. You can connect to the NCBI server, your local BLAST server, or to the BLAST database set up on your own computer. Detailed setup instructions are available in the online help. For additional user control, the BLAST results are analyzed and presented in a simple, succinct format. Select a sequence or an alignment. Then go to the Analyze menu and select BLAST Search or click the button. Choose the desired database by selecting the appropriate genome category. We make every effort to support all the latest databases available at NCBI, including the highly redundant NR database. The filter parameter in Advanced Parameters works similar to the Choose Filter option on the NCBI website. The filter by default is unchecked. When the filter is unchecked, the entire query sequence will be blasted against the selected database. As the database contains regions of low complexity and/or human repeats, they will be reported in the BLAST output as homologous, and the program will avoid these regions when locating primers and probes. Checking the filter will mask off segments of the query sequence that have low compositional complexity, determined by the SEG program, as well as human repeats, lines, and signs. Consequently, they will not be reported in the BLAST output. The program will then search these regions for designing primers and probes, which is undesirable. Please note that NCBI has observed that it is not unusual for nothing at all to be masked by the filter, so filtering should not be expected to always yield an effect. When using a local database, you should set the advanced parameters appropriately. A detailed explanation is available in the online help as well as on the BLAST server. Launch the search by clicking the Search button. When you select an alignment, each sequence in the alignment is BLAST searched against the chosen database, and its status is displayed in the right pane. The Avoid Cross-Homology function is one of the most unique features. It governs which regions of each sequence are avoided while searching for primers. After running a BLAST search for a sequence, open its cross-homology window from the View menu by selecting Cross-Homology or clicking the button. The window shows the interpretation of the BLAST search. The E value represents the significance of each match. The From To column shows the region of the template homologous to database sequences. Clicking the accession number opens its database record for a detailed look. You can see that the interpreter has checked all significant cross-homologies. Of course, you can override any of these recommendations by manually checking or unchecking the boxes. For example, these sequences are checked. They are RNA for 2 receptors and are closely related to the query sequence. The program, therefore, will not design probes in these regions. Note that sequences with an E value of 0 are not checked. These show complete homology with the query sequence and are either the splice variants or a copy of the query sequences in the database. This sequence is the receptor mRNA, which is the same as the query sequence. If you were to check this checkbox, the primer search would fail because the entire sequence would be deemed cross-homologous. To save your selection, click OK. You can BLAST search the primer pair, probe, or amplicon against the relevant database to verify specificity. From the Analyze menu, select BLAST Search, primer pair, probe, amplicon. This functionality is available in all of the modes. For an alignment, all the primers and probes or the amplicons are blast searched against the specified database. Significant secondary structures in the template may prevent the primers from annealing and thus prevent complete product extension by the polymerase. To find the structures, select the sequence. Then, in the Analyze menu, select Template Structure Search or click the icon on the toolbar. Define the search range. It must be no more than 1200 bases. The template is folded at the quick fold server at the temperature you specify or the default of 55 degrees Celsius. Your valid email address is essential for this service. You can view the template structure in your browser. In the View menu, select Template Structure Details. Please note that when locating amplicons, the program avoids stable secondary structures only for single template assays. The sophisticated search algorithm calculates all properties of every possible primer and probe within the allowed length and positional boundaries. Every selected primer and probe must meet all specified criteria. It is rejected if any parameter falls outside of its tolerance limits. The rating indicates how closely a primer or probe meets all the target values. If all parameters are exactly on target, the rating would be 100. On the other hand, if all parameters were out at their tolerance limits, the rating would be 0. The rating therefore depends on how close each parameter is to its target value and how tightly the tolerances are specified. When setting the tolerance limits, the sole criteria should be acceptability. Though counterintuitive, specifying tolerances tightly does not assure better results. A low-rated probe would not necessarily fail. It may be worthwhile to consider its properties relative to your experimental needs and decide whether the probe is acceptable or whether the low rating is an artifact of narrow tolerances. For challenging design problems, the search may fail to yield any result. When a search fails, the rejection statistics for each parameter are shown on the status line. This information is useful for assessing whether different target values or larger tolerances for certain parameters might be appropriate for your experiment. To design Cyber Green primers, go to the Cyber Green Primer Design Assay. Cyber Green primers can be designed for multiple sequences in the same run. To illustrate, select a sequence, then from the Analyze menu, select Primer Search or click the button. Specify the primer length range and the target melting temperature, or you can accept the default values we provide that comply with Cyber Green Primer design guidelines. Options to avoid template secondary structures and cross-homologies are selected by default. The primers are also checked for secondary structures and cross-hybridization. The Advanced Primer Parameter window allows you to specify the maximum acceptable values for self-dimers, hairpins, cross-dimers, and repeats and runs. The default values for secondary structures are set to ensure high signal strength. In this window, you can specify the maximum number of ambiguous bases in the amplicon, primer TM mismatch, or cross-dimer stability. The default amplicon length range is from 75 to 200 base pairs, which is considered optimum for most Cyber Green primer applications. The PCR product can be located anywhere within the template, or you can specify the search range. If the Avoid Template Structure option is selected, the search range is restricted to template regions free of stable secondary structures. To avoid cross-homologies, a blast search will be performed for your sequences. The results will be interpreted and highly specific primers will be designed. Start the search by clicking the Search button. The search quality will be displayed in the Search Status tab. Detailed search results will be displayed in the Primer Properties tab. Click the All Structures button for a graphical view of the secondary structures.